This video is about formula weights, which can also be called formula masses, which could also be called molecular weights, which could also be called molecular masses. And you'll sometimes hear me use these terms interchangeably. And they're all related to molar mass, which is something else that we're going to talk about, not in this video, but fairly soon. The other thing in this video has to do with percent composition by mass of compounds. And so let's just get into it and see what we're talking about. So the formula weight, so if we're talking about a compound, the formula weight is the mass in AMU of one formula unit of that compound. So if we take the chemical formula and we take all of the atoms in that chemical formula, of however many elements there are, however many atoms there are of each element, and we simply sum up the atomic weights of those atoms, that's going to give us a formula weight. So, for example, if we had calcium chloride, which has this formula CaCl2, we're going to take all the calcium atoms, which is one. There's one calcium atom in the formula. We're going to multiply its atomic weight from the periodic table, which is 40.08. We're going to multiply that by 1. It's got 2 chlorines, and so we're going to take the atomic weight of chlorine from the periodic table and multiply it by 2. And then we're going to add those two products together, and that gives us 110.99 AMU. So one formula unit of calcium chloride weighs 110.99 atomic mass units. Now, technically, we use the term formula weight or formula mass to refer to an ionic compound, because ionic compounds are not molecules. And so what we're doing is determining the weight or mass of one formula unit of that compound. If we have so let me just before we get on to molecular weights, let me just talk about a more complex. So that was just calcium chloride, which consists of, the formula unit consists of 2 elements and a total of 3 atoms. Something that's really complex, which is an ionic compound that consists of 2 polyatomic ions. So this is ammonium phosphate. And by the way, just sort of apropos of nothing, but just since it's here, I'll point this out. This again is another rare, fairly rare for this course, example of an ionic compound that does not contain a metal, because the cation is ammonium, which is made up entirely of nonmetals. So while it's true in this course that if a compound contains a metal, it's ionic, it's not always true that if a compound's ionic, then it must contain a metal. And here's an example of an ionic compound that does not. We've talked about the proper way to write these formulas, and this is the proper way to write the formula of ammonium phosphate, NH3 in parentheses, NH4 in parentheses with the subscript 3, followed by the phosphate formula. But for the purpose of calculating a formula weight, actually, we are going to rewrite this by distributing the 3 across the ammonium ion. And so if I need to calculate a formula weight, I'm simply going to take this 3 and I'm going to distribute it. And so I wind up with N3H12. Rather than trying to figure out what the formula weight of ammonium is and then multiply that by 3, I'm just going to distribute it through and rewrite my formula this way. Now that gives me 3 nitrogen atoms, which I multiply by the atomic weight of nitrogen, 12 hydrogen atoms, which I multiply by the atomic weight of hydrogen, 1 phosphorus, which I multiply by the atomic weight of phosphorus, and 4 oxygens, which I multiply by the atomic weight of oxygen. When I sum all those things up, I get 149.1 AMU. So if you have to find the formula weight of something that has a polyatomic ion with a subscript, you really do want to distribute that through to figure out the formula weight. Okay, molecular weight is the sum of the atomic weights of all the atoms in a molecule. And so ethane here is a good example, because if you remember the description we had earlier of empirical formulas, ethane actually has the empirical formula CH3, since you can divide both of these subscripts by 2. but that doesn't represent what's actually in the molecule. And so that's not what we're going to find how we're going to find the molecular weight. To find the molecular weight, we have to use all 8 atoms that are actually in an ethane molecule, 2 carbons and 6 hydrogens. And so, again, for carbon, we multiply the number of atoms by the atomic weight from the periodic table. For hydrogen, we multiply the number of atoms by the atomic weight from the periodic table. We add that up, we get 30.07 AMU as the mass of one ethane molecule. Now, ethane always seems like a relatively boring thing to me, particularly as an organic chemist and former medicinal chemist. So I decided to go for something a little heavier here. This is progesterone, which is a steroid hormone, and I don't know which classes I've discussed this with, but it actually took up a fair chunk of my professional life when I was working as a research chemist, working on progesterone molecules that interact with a protein called the progesterone receptor. And so I'm very familiar with steroid hormones. And I don't expect you to be able to interpret what's called an organic skeletal structure here. And so instead, I'm going to tell you what the formula for progesterone is. It is C21H30O2. So each one of these molecules has 21 carbons, 30 hydrogens, and 2 oxygens. And if you ever get around to learning how to interpret these skeletal structures, maybe I'll buy you a chicken sandwich. Anyway, to figure out the molecular weight of progesterone, I'm going to multiply the atomic weight of carbon by 21 because there are 21 carbons. I'm going to multiply the atomic weight of hydrogen by 30 because there are 30 hydrogens. I'm going to multiply the atomic weight of oxygen by 2. And then when I add all those up, I get molecular weight for progesterone of 314.45 atomic mass units. And in keeping with the drug theme, here is a picture of a compound known as fluoxetine. Known as its brand name that it's sold under is Prozac, so it's for treating depression and anxiety. It has a molecular formula of C17H18F3NO. So if you want to pause the video for a second, try calculating the molecular weight of fluoxetine and then turn the video back on. You can do that. Well, I calculated it to the nearest whole number, and it is 309 atomic mass units. We can do one more, and that would be this compound, which is called celecoxib. It is what's known in the drug industry as a cyclooxygenase 2 inhibitor. It is sold under the trade name Celebrex. It's an anti-inflammatory drug, most notably for treating arthritis. It has a formula of C17H14F3N3O2S. And so if, again, you want to try calculating this molecular weight, you can pause the video and calculate the molecular weight and then turn it back on. So I did it, and to the nearest whole number, it comes out to 381 atomic mass units. Well, once you know the formula of a compound and you have worked out its molecular weight, the other thing you can do is calculate the percent composition by mass of each of the elements in the formula. So you can, in other words, what you can do is if I've got a compound like ethane that just consists of carbon and hydrogen, I know it's 2 carbons atoms and 6 hydrogen atoms, but that's not the ratio of their masses. That ratio of 2 to 6 is just the ratio of the number of atoms. To get the ratio of the masses, I have to take for each element the number of atoms of that element times the atomic weight of one atom of that element, get that product and divide by the formula weight of the compound, multiply that by 100% to get it as a percent. And so going back to ethane, in which we calculated that the molecular weight is 30.07 AMU, suppose I wanted to figure out how much carbon there is in an ethane molecule, what percentage by mass of an ethane molecule is carbon? I'm going to take the first part of that calculation, which is 2 times 12.01 AMU, and now I'm going to divide that by 30.07, which is the total weight. So I'm going to take the weight that is carbon and then divide that by the total weight. And then I'm going to multiply that by 100% to get it as a percentage. And so carbon by weight or by mass constitutes 79.88% of an ethane molecule. Now, when it comes to calculating the percent by mass of hydrogen, I could repeat that same format calculation by hydrogen. The other thing I could do, though, is because I know that the total mass has to add up to 100%, and hydrogen is the only other thing present, I can simply figure out the amount of hydrogen by subtracting 79.88 from 100, which gives me 20.12% hydrogen in ethane. Well, let's try a more complex example. I've got my celecoxib again, which has this hairy formula C17H14F3N3O2S. I am going to do each element using the atomic mass from the atomic weight from the periodic table to 1 decimal place. So for carbon, that's 17 times 12.0 divided by the total molecular weight of the compound, which is 381 times 100%. That gives me 53.5% carbon. Hydrogen to 1 decimal place is 1.0 AMU times 14. That is going to, and then dividing by the molecular weight and multiplying by 100 gives me 3.7% carbon. For fluorine, it's 3 fluorine atoms times 19.0, which is the atomic weight of fluorine to 1 decimal place. Divided by the molecular weight times 100 gives me 15.0% fluorine. I keep doing this the same for the rest of the elements. It's 3 nitrogens times 14.0. It's 2 oxygens times 16.0. It's 1 sulfur times 32.0. In each case here, I've just rounded the atomic weight from the periodic table to 1 decimal place. I get 11% nitrogen, 8.4% oxygen, and 8.4% sulfur. And so I've done all 6 of these elements individually. And when you add all these numbers up, actually, you will find that it does indeed add up to 100. So that's the end of the discussion of molecular weights and percent mass by composition. And so thanks for watching.